Okay, is everybody here? Anyone who's not here, raise their hand. Yeah, we realize for people who don't visit us often, the parking can be confusing, so we're waiting just a couple of minutes for people finding their way from the parking lot. But since I'm the least important part of the show, if they miss me, that's not a big deal. My name is Kenneth Janda. I'm the Dean of Physical Sciences, and so I'm here to officially welcome all of you. It's delightful to see students of all ages. So someone who looks like 2, and some of us are considerably older, so there's quite an age range. I'm glad to hear that you're all interested in physics on a beautiful Saturday afternoon. I think we have a heck of a show for you, involving first some demonstrations in honor of physics faculty member John Rosendahl, who started this event. And then I believe there's going to be some outside demonstrations for a break so everyone can stretch their legs. And those of you who are really dedicated can come back and learn about the recent observation of the Higgs boson. So it's quite an afternoon of physics. And I'm told we have some students from Aliso Viejo Middle School. Is that right? No? Did they get here? They were the ones who couldn't find the parking? Woodbridge High School? Woodbridge? Oh, okay, Woodbridge High School. How about Newhart Middle School? Oh. University High School? All right. Cambridge Prep? Do you have a Cambridge? Anyway, welcome to all the students. We hope you get in the habit of coming to UCI and maybe you want to come back in the future. Also want to really thank the Rosendahl family for their support for coming to this, and especially to Mr. David Mindell, who's helped fund the Physics Roadshow that you're going to see a portion of today. So John Rosendahl and Bill Heidbrink started this Physics Roadshow. The idea is they both do really what some of us call pointy-headed research. That's very hard to explain, but they're also wonderful teachers, and so they put together these demonstrations to help people who don't do physics full-time to get interested in the concepts of physics. And Bill has been a real active member of the community in carrying on John's tradition. So they built many of these demonstrations themselves. Okay. So they visit a lot of middle schools and K-12. High schools too?
Mostly elementary.
Mostly elementary. And I do that occasionally, although now as a dean I don't get to do it quite that often. And the most fun part is the letters you get back from the excited students. And Bill picked one out that I'm going to get to read for you. So, dear Professor Heidbrink, Haley, and Arcana, thank you for coming to my school. I was excited when I heard you were coming, and I really liked all the experiments. The top 3 I liked were the cannon, rocket, and the sailboat. Did you make the experiments? I really wish you could come here every day. I'm going to die if you don't come back. Please come back. So with that, I'll turn the program over to Bill.
Thank you, Ken. So Ken already touched on this program for this afternoon. Adventures in Physics has 4 different parts. The first part is actually an assembly that we perform at elementary schools. And although some of you are children, and I'm glad you're here, I know not all of you are children. Nevertheless, I think that you'll find this very fun, and it does give you a chance to see if you're smarter than a 5th grader. So, this is part of our program. We have a program here for preparing teachers. It's called CalTeach. And so 2 undergraduates who are participants in the CalTeach program will be presenting the assembly for you. All of those assemblies actually end with a hands-on time for the kids to get up and try a few of the things themselves. And so will be our break. That takes us up to around 2:30. Around 2:30, Daniel Whiteson is going to speak for about 40 minutes. We'll have some question and answer. Then we'll have yet another break where most of you will probably want to leave, but we'll have a question and answer time for it's really for high school students, maybe middle school, who have some questions about college, what college is like, and we have an undergraduate panel for that final portion. Okay, with that, that's the plan, and now I want to introduce Haley Steele and Arshna Vestikopal, and did I forget the first person? Okay. They are going to present the show for you as they would as if you were in 4th and 5th grade at one of our schools, and we go out to Orange County schools, often with children who don't have as many privileges as many of us have. So with that, please take it away.
This all? Yeah. Hi everybody, welcome to our physics assembly on motion, why things move. We're going to talk about why things move the way they do. There's two main ways to think about this, and one of the main ways is Newton's laws of motion. And today I'm going to talk about Newton's laws of motion.
And I'm going to show you a different way to look at motion called momentum. And we're going to start off with these slides. We're going to start by reading the words that are underlined. And I'm going to do is I'm going to read it first, and I want you all to repeat after me. Mass. Mass. Velocity. Velocity. Momentum. Momentum. Conservation. Conservation. You guys are so good. Okay.
Oh, they're looking at me like,
Yeah. So the first one that we're going to talk about today is mass. Mass is the easiest one to understand. Mass is the amount of matter in something. So this beach ball doesn't have much mass. It's really easy for me to lift up. But this medicine ball has a lot more mass. It's a lot more difficult for me to lift up. Something with a lot of mass is hard to get moving, but something with a lot less mass is easier to get moving.
And mass also matters when something's already in motion. So let's say I throw this beach ball at Haley.
Just a minute, Archie. Put it a little higher. Yeah,
Can you back down?
I think so.
No? Technical. Not good? Reject. I'm just going to talk really loud.
Okay, good.
Okay. So, mass also matters when something's already in motion. When I toss this beach ball at Haley, it's easy for her to stop it because it doesn't have a lot of mass. But when she throws the medicine ball,
Ready?
no. It's a lot harder for me to stop because it's a lot harder for me to stop because it has a lot more mass compared to the beach ball.
This is Newton's idea, first law of motion. Something in motion stays in motion unless a force stops it.
Like me.
And something sitting still continues staying still unless a force is applied to it. I don't know how you guys do this.
Yeah, we're used to a small group of kids and all kinds. Yeah. Our next idea is velocity, and there are two parts to velocity. The first one is how fast something's moving. The second is what direction it's going in. So let's say I start falling this way.
You went too far.
Right now, I have a small velocity in this direction. Let's say I get up and start running. Then I have a bigger velocity in the same direction. Let's say I turn around and start walking casually this way. Now I have a medium velocity in this direction.
As you can see, Arshna demonstrated what this baby's showing us. She was going in that direction at a very slow velocity. So her velocity, we're going to say, is 1, like the baby. And you can see that that is denoted by the small arrow. The arrow represents the amount at which she was going, or the magnitude. And the second baby is moving a lot faster, so while Arshna was running in that direction. So it has a much greater velocity, which we're going to say was 5. And you can see by the arrow, it's a lot longer than the first one. So it has a much greater velocity. And our third baby, Arshna demonstrated this by turning around and going in the opposite direction. But this baby is actually jogging backwards. So its velocity is a medium velocity in the opposite direction. And we denote this opposite direction with a negative number.
Our next idea is momentum, or mass in motion. So, right now, this beach velocity, so it has a big momentum. And as you can see, in science, we use letters to symbolize the words and the concepts. So M represents mass, V represents velocity, and P represents momentum. So we're going to do some science math problems because math is really important, especially in science. The two go together all the time.
Also in science, we like to use symbols to represent what we're talking about. So our mass, we use M to represent this. Velocity, we use V. And in this case, we're in momentum, we call that P. So our first situation is a beach ball, and it's moving in that direction with a velocity of 2 and its mass of 1. Momentum is equal to mass times velocity. Can you guys all tell me what our momentum is in this case? 2. Great. So 1 times 2 is 2. So our momentum is in that direction, and it's also shown with the arrow.
Our next problem is the same beach ball, but now it's moving a little faster. So we're going to say the velocity is now 5, and the mass is still 1. So what's our momentum? Good job. Yes. Our momentum is 5.
Our third situation is actually a medicine ball. So the medicine ball is, we're going to say, is 10 times heavier than the beach ball. It has a mass of 10. But like the first situation, it still has a velocity of 2. What's our momentum of the medicine ball in this case? 20, yes. So you guys can see that they are moving at the same speed, but our medicine ball, since it has more mass, has a lot more momentum. And this is also shown with our red arrow. It's a lot longer.
And our last example is the same beach ball, but now it's moving in the opposite direction. So again, to symbolize that, we put a negative in front of it. So our velocity is -5, our mass is still 1, so our momentum is -5. Good job. Yes. And we show it's going the opposite direction by the arrow and the negative sign.
Okay, so when I turn on this air trap down here, this is going to represent our car, like our car in our little picture right here. When I turn on this air track, this car is floating on our air track. It's easy to move. So Newton's second law of motion is applying a force in order to change its momentum. So when I push on this cart this direction, I'm applying a force on the cart this way. So its momentum is being changed going this way. When the cart gets down to the end, this elastic applied a force, I'll do that one more time, onto the cart this way, now changing the cart's momentum. It is now going this way.
So this is our last idea before we show you some really cool demonstrations, and it's the idea of conservation. In science, when you conserve something, it means you save it. It doesn't go away. It's not wasted. So what Haley's going to do is she's going to show you how a system of objects conserves momentum before and after an event.
So our first situation is an elastic collision. This is a collision where the objects are bouncing off of one another. So we have our first car. Our first car is going to be at rest. It has 0 velocity. And our second car is going to be in motion.
I think our second car is getting its elastic band, so it's really elastic.
Okay, here we go. So once again, our first car has 0 velocity, and our second car is going to be moving in this direction, and we're going to see what happens. As you guys can see, this car stopped right when it hit this car, and this car continued in the same direction with the same velocity that the second car had. Archie is going to describe a math science problem to us, because math is really important in science.
Did we say that already, that math is important in science?
When we do these demonstrations at elementary schools, we really like to emphasize that math is important in science.
So, like Haley was showing us, the first car was at rest, so it had a velocity of 0, and we're just going to say that the mass is 1. So what's the momentum if it's 0 times 1? 0! Not all of you said it, but good job for that. Our second car has a velocity of 2 and same mass of 1. So what's the momentum, everyone? 2. Good job. So our momentum of the system, which is the 2 cars, is 2 plus 0, which is 2. And with the idea of conservation, the momentum before should be equal to the momentum after. So what is the momentum after going to be if the momentum before is 2? 2. Be confident, that's right. So after, like Haley showed us, the second car that she pushed stopped. It had a velocity of 0. So now that has a momentum of 0. And the first car, which was originally at rest, moved off. So now that has a velocity of 2 and a momentum of 2. So the momentum of the system is 2.
Our next situation we're going to do is an inelastic collision. So this time, instead of the cars bouncing off one another, they are going to stick together. But we're going to make sure that we understand that we're doing the same scenario as last time. This car is at rest, our first car is at rest, our second car is going to be in motion towards it, and they're going to stick together. In science, we like to make predictions about things.
So that's called a hypothesis. When you make a prediction about something happening, we're making a hypothesis. And that's what you guys are going to do today. So we have 4 options for what's going to happen. When Haley pushes the car, are they going to stop? Are they going to move off in that direction at the same speed as the original car? Are they going to move off in that direction but slower? Or are they going to move off in the opposite direction? So I want you to raise a finger for which option you think it is. 1, 2, 3, or 4. All of you raise your fingers.
So 1 was they move off in the same direction with the same speed. Number 2 was they move off in the same direction with a lesser speed. Did I mess that up?
No, you got it right.
Number 1 was they stop. Number 2 was they move off in the same speed. Number 3, a lesser speed. Number 4, they go in the opposite direction.
So raise your fingers.
So you guys are all making your hypothesis. Okay, let's go ahead and see what happens. So this car is stopped, and this one's going to be in motion.
So if you put up 3, you were correct. Good job.
Yay!
This also works if the car is moving much faster. So I'm going to apply a little bit of a greater force on this car, and it's going to have a greater velocity. As you can see, they still move off with a smaller speed.
Again, I'm going to show you this in terms of math because math is really important in science. So, the first car, just like she had it before, is moving, but now it's moving faster. So we're giving it a velocity of 10. The masses are still 1. So the momentum of the first car is 10. The momentum of the second car, which was at rest, is 0. So the total momentum of the system is 10 plus 0, which is 10. So the momentum before is 10. What's the momentum after going to be? 10. Good. Look at you guys. So, since we know the momentum after is going to be 10, since the cars are now combined, their mass is now 2, because 1 plus 1 is 2. And we need to figure out what velocity will give us the momentum of 10. That's why the car is slowed down. It needs a velocity of 5, which is half the velocity it had before, to keep the conservation of momentum.
Okay, so our third situation is also an inelastic collision. But this time, instead of one car being at rest, they're both going to be in motion. And they're going to be going towards each other. Once again, we're going to make a prediction, because making a hypothesis in science is also important, about what's going to happen.
We're going to have 3 options. First option is that they stick together and stop. The second is that they move off in this direction, slower, or at the same speed. And the third is that they move off in the opposite direction. So raise your fingers again. Which option do you think it is? There's only 1, 2, or 3. No 5.
Okay, let's go ahead and see what happens. So you guys saw it all basically stop. Let's see if I can do it perfectly. At the end of the show, we'll have you guys have an opportunity to actually work on this and see if you guys can do it better than me. I'm going to do it one more time and see if I can get it perfect. Pretty cool. Now we're going to talk about the math behind this problem.
So for this, instead of moving at the same direction with one car stopped, they're both moving at opposite directions. And like we said before, to symbolize opposite direction, we're going to use a negative. So we have the first car with a velocity of 2 and a mass of 1, so that's the momentum of 2. And the second car has a velocity of negative 2, because it's going in the opposite direction. So that has a momentum of negative 2. And in math, when you add a negative, that's like subtracting. So 2 plus negative 2 gives you a momentum of 0. So the momentum before is 0, the momentum after is 0. And what you have is the two cars stick together. Again, the mass becomes 2 because of the individual cars. And the momentum is 0. So what velocity gives us the momentum of 0? 2 times what gives you 0? 0. Good job. So we have the velocity of 0, which is why the two cars stopped. So now I'm going to show you a really cool demonstration with 2 cars attached by a spring. And this is what I'm going to do. I'm going to put this on the track. This cone will represent the middle, and I'm going to stretch them apart the same distance and let it go. These both have equal masses, as you can see, hopefully. And I want you guys to make another prediction about where you think these cars will crash. So raise your hand. The 3 options are they crash on this side by the red car, they crash in the middle, or they crash by the blue car. Raise your hand with the option that you think it's going to crash.
Okay, let's check it out.
You ready? You all see it? Where do they crash? In the middle. Good job. Whoever had 2 up is correct.
Awesome. I wonder what's going to happen if one is heavier than the other.
Let's find out. So what I'm going to do is, I'm going to take out one of the masses from the car. And now I'm going to do the same thing I did before. I'm going to pull them apart and let them crash together. Now I want you to make another hypothesis about where you think it's going to crash. So again,
Before you do the options, which one's heavier?
heavier car is on this side, the red car. The lighter car is on this side, the blue car. So the options are they'll crash here by the heavier car, they'll crash in the middle, or they'll crash here by the lighter car. Go ahead and raise your fingers. Interesting, we have a mix. Okay, so let's find out. Same thing. You guys all see it? Where did it crash? By the heavier car, yeah. So if you had option 1, you were correct. Good job.
Cool. Want to replay that one more time?
Yeah.
So as you guys go ahead and look up, we have a demonstration right here. So you guys can see it crash closer to the truck. The reason this is because the truck has a greater mass, which is why we have a large M, and our race car has a smaller mass, which is why we have a small M. Our truck has a much smaller velocity because we're conserving momentum. Momentum has to be conserved, so they must be equal. So for that to happen, our velocity of our truck is much smaller, but our velocity of our race car is much larger, which is why it crashed closer to the truck.
So since it had a larger velocity, it traveled further. And that's where you have it by the heavier car. And now we're actually going to do this demonstration with
Our volunteers.
volunteers.
Can we have our volunteers go ahead and come on up, you guys?
So Jonathan and
They've already been selected.
Jonathan and Sarah.
Okay.
Don't worry, you guys will have an opportunity too. We'll do this after.
This is one of the things that we do during the hands-on part.
Okay, Sarah, you want to sit right here? You're going to sit right here. Just on your pause. You can sit right in. You're going to do this perfect. Sit right there, okay?
So right now, while they're all sitting still and not moving, how much momentum do Sarah and Jonathan have?
0.
Good job.
Right there. We're going to hold this side. Okay, so before we go ahead and go, we have one more thing to talk about. Newton's third law of motion. So Newton's third law of motion states that we have to, forces come in action-reaction pairs. So I'm applying a force on Archna right now, and she's also applying a force back on me. But if I try to apply a force on Archna, and I can't apply that force, then she can't apply a force back on me. Okay? So Sarah, what you're going to do is just hold your hand open like this. Don't hold on to the rope. Don't grab, okay? So we're going to see what happens. On the count of 3, you're going to pull really hard, okay? Just let it go, okay? 1, 2, you're just going to stay right there.
So you can leave your
Leave your hands right open. You pull it really tight. Pull really hard, as hard as you can, Jonathan. 1, 2, 3, pull. What happened? Nothing. Nothing happened because Jonathan was applying force, but we didn't have an equal and opposite force from Sarah. So let's go ahead and try that again. Oh my goodness.
But this time, Sarah, you pull real hard.
Okay, let's
Both
get
people
nice and
pull real
taut.
hard.
You're gonna pull too.
Both are going to pull real hard.
Okay, on the count of three, you guys ready? 1, 2, 3.
Go, 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 go.
Caleb, you guys want to try one more time?
Yeah.
Okay, let's back it up a little bit.
Harder this time.
Okay, pull like this.
Okay.
Okay?
It's like tug of war.
Okay, really hard. As hard as you can.
Okay,
1,
count out with him. 1, 2,
3. Yay! Awesome. Thank you guys so much. Let's have a round of applause for our volunteers. She dropped it. Okay, so we can see by our cans crushing is that we had equal and opposite forces happening. I don't know if you guys can see from up there. We had cans in the middle of our collision car. And by the crushed cans, it shows that we had equal and opposite forces. So this is, yeah. Okay, so we also have this demonstration where we have a basketball. So it has a lot more mass than our handball. Okay, so we're just going to see what happens when, I don't know if I can balance this perfectly. When I drop this basketball downwards. We see that the handball flew up, but the basketball didn't move very far or very fast. As you guys can see in the picture, the basketball has a lot greater mass, which we have a large M once again, and our handball has a much smaller mass compared to the basketball, so it has a small m. In order for conservation of momentum to take place, we have to have the handball must have a large velocity, and the basketball must have a small velocity. And they are still applying equal and opposite forces on one another.
So you have both Newton's forces and momentum happening in that interaction. Next, we're going to do a really cool example using this car.
Are we going to do the rock? Oh,
Rocket?
So we have another really cool demonstration. Professor Heidbrink's actually going to do this one, and it's our rocket.
okay. So we have a bottle here that has some water in it. If you put a small amount of water, it will go really high during the hands-on portion. One of the options is to go outside and watch it go really high. But what we're going to do right now is I put enough. I think I'm not going to hit the ceiling. We'll see. Sometimes it only goes about as high as my head, and it's disappointing. We'll find out. This is another example, though, of it's going to start from rest. So I push the cork in so it's nice and tight. And it's going to start from rest. So how much momentum does my rocket and water have right now? 0. Good. So it's going to be the same thing, that they're going to have equal and opposite momentum, and they're going to exert equal and opposite forces on each other when the rocket shoots off. So I'm now going to pressurize the water rocket. And so, of course, because the rocket is light, it goes really up very high. Because it has a small m but a big V.
So we're not going to tell anyone that it hit the ceiling. Or is it his head public current?
So our next, we're going to do the sailboat.
Are we going to do the sailboat next?
Yep.
As cannon's last?
Yeah, okay. So, this is a car that's going to represent my sailboat. When I turn on the fan, we have air pushing out this direction. And remember how we're making hypotheses? We're going to do it again. I'm going to put this car on the track with the fan turned on. I want you to tell me which direction you think the boat will go. Do you think it'll go that direction? Do you think it'll stay still? Or do you think it'll go in that direction? So raise your hands. Everyone.
So our air is blowing that way.
Oh, okay.
Sorry.
Okay.
So it's just a boat right now, not a sailboat. This is our sail. We'll put that on later. So it's a boat, and the air is blowing that way. We'll give them their options one more time about which way the boat will move.
The first option is it'll move this way. Second option is it'll stay still. And third option is it'll move this way.
Make your guys' predictions. Okay, let's see what happens. So if you guys predicted it would go this way, you guys are correct. The reason is because the force of the air is blowing the boat blowing this way, but the air is also pushing with an equal and opposite force on the boat that way. Okay? Conservation of momentum.
So air pushes one way, boat pushes the other. Now we're going to make it a little bit trickier by adding the sail to it. So now we still have air coming out, but think about what direction it's going.
So our air is still blowing this way.
Moving this way.
We're not going to give you guys any more hints. You guys are going to predict what you think. Do you guys think?
Same options. Will it move this way? Will it stay still? Or will it move this way? So raise your fingers.
Hold up your guys' predictions. Okay, let's see.
Okay. It's moving slowly, but it's moving this way. So those of you who picked 3 are correct. It moves that direction.
Okay, so what is happening is our air is still blowing in this direction, but now it's hitting this sail. So when it hits the sail, the air is now going this way. But we know by Newton's third law of motion, equal and opposite forces, what direction is our force going now? This way. So that's why our boat is moving this way.
So the force of the boat on the air is to the left, but the force of the air on the boat is to the right.
And that's why the boat moves to the left.
And these, the momenta are equal. Okay,
Next.
now is it the cannon?
I think so.
Okay, now we have one final
Go ahead,
really
Kenneth.
cool demonstration. You can guess what it is. Yeah, it's a cannon. Aw.
So this is our cannon. And this bottle is going to represent our cannonball. And this is liquid nitrogen. Arch is going to go ahead and tell us about liquid nitrogen.
So liquid nitrogen is really, really cold. It's so cold, it has a really low boiling temperature. So right now, when Haley's pouring it in, it's actually boiling. So you guys see the steam coming out? It's because it's boiling. So if you touch it, it will actually
Put a little more
burn
in,
you.
Haley.
More?
Yeah,
So that's what Haley is trained.
that's good.
She knows how to deal with liquid nitrogen. If you guys ever come into contact with it, be very careful.
Arch, will you hold the back of our catapult? So I'm just going to go ahead and pound our catapult.
You hear the hissing noise? That's the gas escaping.
Okay.
Oh, come on, Haley, a little more.
More.
I'm just trying to destroy the room if you can tell.
Okay.
Level it out. Aim at the audience. Now you're supposed to watch to see which way the cannon. The bottle's going to go that way. Which way will the cannon go? Because that's conservation of momentum and it's equal and opposite forces. That's better. All right.
As you guys can see, the catapult has a much greater mass than the cannonball itself. So our cannon has a large M, and our cannonball has a small m. So conservation of momentum tells us that we have to have, momentum must be conserved. So in order for that to happen, our velocity of our cannonball must be much greater than our velocity of our cannon, which is why the ball gets shot off really far, normally, if your ball's not broken.
And
But
also have forces applied to it because the cannon is giving a force to the cannonball, and the cannonball is giving a force to the cannon. But since the cannon's much bigger, you don't see that force as much. It moves back a little, but not as much as the cannonball shoots out.
Okay.
Okay, now we're going to make sure you guys are paying attention because we're going to have a little review. Okay, so the first question is, what is mass? Really tricky. First option, the amount of matter or stuff in something. Second, how fast something is moving. Third, something heavy that is moving fast. You guys already have your hands up. Look at you.
While we're waiting for everyone to make their prediction on what the answer is. Okay, let's see.
Good. I saw a lot of ones. Most of you were correct. It's one. It's how much matter or stuff is in something.
So velocity, let's go ahead and go over what 2 and 3 are. Velocity is how fast something is moving. And something with a large momentum is something that is heavy that is moving fast. We have one more question for you guys.
A rifle fires a bullet. What is the same afterwards? Is it A, the mass of the rifle and the mass of the bullet are the same? Is it B, the velocity of the rifle and the velocity of the bullet are the same? Or is it C, the momentum of the rifle and the momentum of the bullet are the same, but in opposite directions? So raise your fingers. 1, 2, 3.
Those of you who picked 3 are correct. So the momentum of the rifle and the momentum of the bullet are the same. Conservation of momentum. So as you guys can see in our picture, our masses aren't the same. Our mass of our rifle is much greater than our bullet, and our velocities aren't the same. Our velocity of our bullet is much greater than our velocity of our rifle. But they still have equal and opposite forces acting on one another.
So that concludes the demonstration part of our assembly, and we're going to have a really fun hands-on part after.
Okay, so this is an opportunity to get up and move around. If you need to use the restroom before Professor Whiteson starts his talk, you can actually go out the doors, and just to the right are some and to the left as well. There's some restrooms there. We have a lot of hands-on activities. So, Haley, what can people do with you?
I'm going to be up here with the air track, and you guys can go ahead and work with elastic and inelastic collisions.
Archana, what can people do with you?
I'll be over here with the carts that you saw earlier, so if you want a chance to get on it and action each other, come to me.
Or, just a minute, we also have these, which are like our air track collisions. You can let one ball go and see what happens, or 2 balls, or you can have them come from opposite directions, pulling on each side. These are set up all around. I do ask that you treat them gently, because when they get tangled, it's really hard to untangle them. So parents, please keep an eye on your kids so they don't go like that. And then the fourth option is I'm going to take the water rocket outside and shoot off the water rocket. And that will be right out in the courtyard out there. So we will come back we'll have 15 minutes for this, so we'll start at 2:25 with Professor Whiteson's talk about the discovery they did. Part of our program is about something that relates to momentum and momentum conservation. But this now we're turning to some of the research at our university. We're a research university, so I don't just go out to elementary schools. We teach college students, and we also do lots of research. Our speaker today is Professor Daniel Whiteson. He received his Ph.D. from Berkeley a little over 10 years ago. He has won many awards. He has a Sloan Fellowship, a Fulbright, and another one that I forgot. Oh, the DOE, Department of Energy Junior Investigator one. So those are the kinds of things that get you promotions at the university. But he has another claim to fame, which is that he is a collaborator on webcomics, and so he's done one about the Higgs and about dark energy and extra dimensions. So, Daniel, take it away.
All right, thank you, everybody. Thank you for that invitation. And thanks, everybody, for coming out. That was really an amazing show, guys. I haven't seen that one before. It was wonderful. So I'm grateful to get to talk to you guys about my research. It's something I'm really interested in. And I'm grateful to you for coming and showing your interest. I'm always amazed at how much interest there is by the general public in a sort of in a very esoteric corner of physics, which is particle physics. Now, what you're looking at here, this video I put up for your enjoyment, is the assembly of the Atlas detector. And I'll tell you a lot more about it later, but this is one of the biggest machines ever made by man, and it was put together over about a 15-year period by a team of thousands of graduate students and postdocs. It's been compressed down to about 30 seconds for your enjoyment, and you can see the whole thing has been assembled. And it's interesting how much attention there is in particle physics. There is attention not just scientifically, but also in a popular sense. And I'm particularly gratified to see, for example, particle physics appear in the New Yorker. So this is a comic from the New Yorker. Frequently asked questions about the Hadron Collider. And it's pretty funny. It's like, how does the Hadron Collider work? Well, you didn't even understand 11th grade math, so why are you asking? Right? Stuff like that. Or, what would happen if you put a cat inside the Large Hadron Collider? Answer, I don't know. All right. Now, and it's funny to see this in the popular culture. This sort of plays on the joke that everybody feels like, ha ha ha, I could never understand particle physics, right? We all spend our taxpayer dollars to build this thing some people are playing with, we could never figure it out. And while that's a funny joke, I'm hoping that today I can convince you that you can understand it. Because the interesting thing about particle physics and the interesting thing about the Large Hadron Collider are not the technical details, but the basic motivation, why we're doing it, and the answers that we get, what we learn about the universe. And so that's what I'm going to try to show you today, how we use momentum at the Large Hadron Collider to explore the universe around us. And for me, science is about exploration. When I was a kid and I was learning about all the people sailing around the world, discovering new continents, I thought that was awesome. I thought, I would love to figure out something new. I would love to be the first person to step on a new continent, the first person to land in South America, the first person to reach the South Pole. That would be really exciting, right? But in this modern day and age with satellites and everything, we basically figured out where everything on the Earth is. And so you feel sort of like everything's used up, right? You can't get in a ship and go off and discover something unless it's a tiny new island. But it turns out that's not true. You just have to look a little harder. There's a huge amount of exploration left around us. It's just not the same kind of exploration. And it's the exploration of the universe, figuring out what everything is made out of, understanding how everything works, all right? So what do I mean by exploration? What do I mean by figuring out how things work? I'm talking about tapping into the basic questions that we have. The questions that everybody wants to know the answer to, even if you're not a particle physicist. Basic questions that people have been asking since there were people. And I'm talking about the kind of questions like my 4-year-old asks me, you know, questions like, why are we here? Who are we? What is it like to be a bat, right? Basic questions we all ask. And if you're laughing about that one, this is actually the title of one of the most cited papers in philosophy ever. Not a joke. So these are important questions, questions we all want to know the answer to. Questions if we knew the answer, we feel like it would change our relationship with the universe, right? Now these are philosophical questions, and so not really probable by modern science, but there are other questions I think are at the same caliber of importance, the same level that everybody can understand, right? Questions like, what are things made out of? How do those things interact? Why is there anything rather than nothing? What is mass anyway? Where did everything come from? What is the future of the universe? These questions in my mind are as big as the other questions, maybe even more important. And the difference is, these are physics questions, which means we can make hypotheses, we can do experiments, and we can learn the answers. These questions have answers that we can figure out just by doing experiments and being clever and building massive toys underground in Switzerland, right? So this is what's exciting, is that there is still exploration left to be done. There are questions out there that are fascinating to anybody, everybody. You sit on an airplane next to somebody, they ask me, what do you do in particle physics? They say, whoa, what does that mean? I can tell them we're answering these questions, right? So let's talk in more depth about one of these questions that I think is the most interesting, and that's this one. What is the world made out of? A question people have been asking themselves since cavemen took 2 rocks and broke them together into smaller rocks, right? And wondered, how long can I break this rock into smaller and smaller rocks, right? Now, imagine you're the first person to ever think of this question, okay? And your job is to figure out what the universe is made out of. And nobody's ever thought about this before. What would you do? Well, you start out just looking. What is around me, right? Start cataloging the things you see. And there's a lot of different stuff out there, right? And very quickly you discover that the universe has rocks, it has people, it has Sundays, you know, it has all sorts of stuff. And it's an overwhelming diversity. It's amazing. Our universe is full with an almost infinite variety of stuff, right? Which makes it very difficult to categorize, to understand what everything is made out of. But you're a good scientist. You're going to tackle this question dutifully. So what you're going to do is try to organize everything, right? You say, well, I'll put all the plant-like stuff over here. I'll put the rock-like stuff over there. I'll put the electronic toys over here. The people stuff over here. And you can argue about whether Arnold Schwarzenegger belongs in the people category or the thing category. Okay? But everything has to be in a category, right? We're doing science. Okay? It's got to be fixed and rigid. But what you discover pretty quickly is that there's a lot of stuff, and it's not easy to categorize, right? Now, zoom forward a couple of thousand years, and you achieve this. Right? This is about 150 years ago, 200 years ago. We achieved the periodic table. Now, you look at the periodic table, it might seem sort of dry. You're like, well, why are you showing me the periodic table? Well, the periodic table is an incredible step forward in this question of what things are made of. You go from a list, basically a list of everything in the universe, a near infinitely long list, to a list of about 100 things, from which you can make anything anybody's ever touched, tasted, seen, heard, interacted with, thought of, can be built using these 100 basic building blocks. That's an incredible step forward, right? From near infinite down to 100. Huge progress, all right? And this is 200 years ago. So that's an incredible insight that the universe is made of smaller things which can be assembled to build the things we're familiar with, right? And you look at this list, you look at this periodic table, and you notice there are patterns, right? And some of you who've taken chemistry know that some of these things are very reactive, and some of these things are very stable, and some of these things are metallic. And I mean, I'm not a chemist, but I know that there are patterns here in the periodic table. And if you look at them, you wonder, why are there patterns? What do these patterns mean, right? And this is why we do science. We carefully categorize all of our information. We look for patterns because those patterns are clues. They're clues that maybe this description is not the simplest. It's not the final answer. Maybe underlying this periodic table is a simpler idea of which those patterns are clues, right? And now we know that all of the structure of the periodic table comes from how electrons fill up the orbitals around the nuclei. So each of these elements in the periodic table have a different number of protons in their nucleus, and so a different number of electrons orbiting them. And how those electrons get filled determines whether something is active or not active, and all of its chemical properties. So the structure of the periodic table comes from a simpler idea. It comes from the structure of the atom, right? Now, if you look inside the atom, you see the atom has electrons whizzing around, and in the center of the atom is the nucleus. The nucleus is made out of protons and neutrons. Your protons are orange. In real life, they don't really have a color. The neutrons are blue. And if you open up one of these nucleons, a proton or a neutron, you find something else inside. You find quarks, up quarks and down quarks. So with up quarks and down quarks, you can make protons and neutrons. Sprinkle some electrons around, and you can make an atom. Put those atoms together, and you can make pigs, iPhones, supernovas, anything, right? So we've taken even another step forward in this quest, right? We've gone from 100 elements we thought were good basic building blocks, and we've discovered that with just 3 kinds of particles, up quarks, down quarks, and electrons, we can make all of those building blocks. So now we've gone from near infinite to about 100, down to 3 particles. With 3 particles, we can make anything we've ever seen, touched, or tasted, right? Well, it feels like the answer's almost around the corner, right? We're basically done. We'll figure it out next week, right? Seems like good progress. But there are wrinkles in the story, okay? Even though it seems like these particles are almost the final answer in this question, it turns out there are more particles, okay? Linus Hall, which is just around the ring of our physics building, is named after Fred Linus, who discovered the neutrino. The neutrino is a ghost-like little particle that hardly ever interacts with anybody, but it's everywhere. There's millions and trillions of neutrinos being shot at us from the sun as we speak, but they fly right through us without us hardly feeling them. A single neutrino can go through a light year of lead. A light year is how far light travels in a year, which is very, 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 very far. Now imagine a light year of lead, okay? A neutrino can fly right through that. It hardly ever interacts. So why are there neutrinos, right? Why do we have neutrinos? We don't know, but they're there, so they're part of the clues, right? And if you keep looking for particles, which is my job, to keep looking for particles, you find that the up quark and the down quark are not the only kind of quarks out there. There are other kinds of quarks with even sillier names. Charm, strange, top, bottom, sometimes called truth and beauty. And I'm not on the committee to name these particles, unfortunately, or name them all after my children. But the weird thing is that the charm quark and the top quark, you write them in a row next to the other ones because they're exactly the same as the up quark, except that they're heavy. So it's like the up quark has two cousins, a fat cousin and a super fat cousin, all right? And you almost never see them because they're too fat to leave the house, but they're there. The down quark also has two fatter cousins, and all of these guys have two more cousins. Why are there these other particles out there? You don't need the top quark or the bottom quark to make hydrogen or to make ice cream or anything. You never see it. You don't need these other particles around, but they're there. They can be made, right? They're on the menu of particles which exist. And now you notice what I've done here is assemble a new periodic table, a periodic table of the fundamental particles. Why did I do that? Well, for the same reason we made a periodic table of the elements. I'm hoping that by assembling our information here, we will notice patterns. Those patterns will lead to questions. Those questions are clues, hopefully, to understand a deeper, more fundamental theory of what's going on in the universe. Right? In 300 years, people will look back and say, oh, that's because they didn't know that the truth was whatever the truth is. So we found these 12 particles, right? And there are lots of questions like, how many particles are there? Are there only 12? Are there a billion? Right? We have no theoretical limit on the number of fundamental particles. None. We've made 12 so far. That doesn't mean there aren't a billion. We don't know, maybe there's just 13. We have no idea if this is the tip of the iceberg or just an ice cube. Why does every particle have exactly two cousins? We're pretty sure now that there are exactly, we call them generations of particles. 1, 2, 3. We're pretty sure there are exactly 3. Why 3? 3 is sort of a strange number. If you look for mathematical purity, right? If your goal is in the end to write the equation of the universe on a t-shirt, right? A very simple expression for the whole universe. Then you want to have simple numbers in there. Mathematicians will tell you simple numbers are 0, 1, maybe pi, maybe e, right? But 3 is a sort of a strange number for that, a fundamental number of the universe. Unless you're Catholic and you believe that 3 is fundamentally important to the universe, then maybe that's a clue. But it's an interesting philosophical implication, right? Everything we discover, if it turns out to be fundamental, has interesting philosophical implications because what we're trying to do is understand what's underneath, what's inside, what's making up everything in the universe. All right? We're also curious about why are there 6 of these particles in the bottom, blue, called leptons, and 6 of these guys called quarks. Remember, the quarks will make up the proton and the neutron, and the electron whizzes around. According to our current theory, there's no relationship between these particles. None at all. Right? Now, obviously, there should be some relationship because the electric charge of the proton exactly balances the electric charge of the electron so that you can have an atom. Right? If those two were different by 1 part in 10 to the 10, you would not have stable atoms. But according to our current theory, that's a pure coincidence. Right? That sort of seems like a hint. Maybe there's something going on. These two beings are two sides of the same coin. There's some relationship there, right? It's unlikely to have such a crazy coincidence. Why do these particles have such strange masses? I've told you that they get heavier, but there's no apparent pattern to why they're heavy. We use these units in particle physics called GeV. Approximately 1 GeV is the mass of a proton. So you see an electron is very, very small, 10 to the negative 4 GeV, while a top quark is almost 200 GeV. A single particle, this fundamental particle, a top quark, weighs as much as a gold atom, right? And the spectrum, look, it's 10 to the 6, difference between the smallest and the heaviest. We don't understand why there's such different masses. So there's lots of questions. I haven't even addressed the questions about the different forces. There are other particles, photons, WZs, gluons, and of course the Higgs boson I'll talk about more, that connect these particles and teach us how they interact. But we just don't really understand a lot about these patterns. Now, we have a theory. It's called the Standard Model. And the Standard Model is a beautiful theory. It works very, very well. It's extraordinarily precise. It predicts all the particle interactions that we've seen, and all the experiments we've done have confirmed the Standard Model. And it's a very precise theory. In fact, there's one calculation that you can do in the Standard Model, which you can also measure in an experiment, and it gets it right to 11 decimal places. So the theory predicts that you measure a certain number to 11 decimal places, and the measurement verifies each of those 11 decimal places. It's amazingly precise, right? It's super precise. It's so precise you might think this isn't just a prediction, maybe it's actually what the universe is using to do the number, to do the calculation, right? I mean, the chance that you can get that kind of prediction accurately correct by chance is like the chance of hitting a golf ball in New York and getting a hole-in-one in China. I mean, it's just impossible for it to be an accident. So we think we're onto something. But you can also judge a standard model not just by how effective it is, but by its simplicity, right? Because remember, what we want to do is put the standard model on a t-shirt. We want to say, here's the equation of the universe. And so this is the expression for the standard model. It's actually half of it. I couldn't put the other half on. And you can ask yourself, is this the fundamental theory of the universe? Is this the final answer? And I would say that, this can't really be the final answer. There must be a simpler explanation. And I think of it like this. I think we're probably just speaking the wrong language. Because, when you're speaking the wrong language, things look complicated. Like these scientists who are listening to the dolphins, and they're writing down phonetically, que pasa, habla español. And they have no idea what they're hearing, right? Because they don't speak Spanish, and so nothing makes sense to them. They have to write it down phonetically and record all the details. In the same sense, maybe we're just looking at things in the wrong way. Maybe we're using the wrong mathematical notation. Maybe we're thinking about things the wrong way because of our personal experiences. And that's making it much more complicated than it needs to be. And if we had a new idea, a new way to write things down, a new way to organize our thoughts, it would just snap into place, and suddenly we would realize we could just speak Spanish to these dolphins, right? Okay, now, I told you that we've made great progress in understanding matter, and that's true. But we've recently learned that the kind of matter that we've been studying, protons and neutrons and all that stuff that we spent 300 years studying in detail, turns out that's a tiny fraction of the universe. So if you made a pie chart of all the stuff in the universe, the kind of stuff that we are familiar with, the things that make up planets, stars, ice cream, all that stuff, is about 5% of the whole universe. Is there a question?
Okay, what are those red blocks? What do they stand for?
So these guys, let's see if I have a pointer here. So these are the quarks. These are the leptons I told you about. These are particles I didn't have time to tell you about, but they carry forces. So this is a photon. It carries for particles of light. This W and Z boson. They're a lot like light, but they're very heavy. They have mass and they carry the weak force. These particles are gluons. They're what's responsible for holding the nucleus together. So these guys, all these guys that fit together, we have some grasp of, some understanding, though of course not complete understanding, only describes 5% of the universe. Right? Most of the universe is something else. 20% of the universe is something called dark matter. We know it's out there. It doesn't reflect light. It doesn't emit any light. It's dark. It's mysterious. It's heavy. There's a lot of it. And that's about all we know. And the rest of it, so that is 25%. The rest of it, 75% of the stuff in the universe is something we call dark energy. Now, dark matter and dark energy have no relationship except for the word dark. Okay? Really, dark energy really just means, is scientific code for we have no idea what this stuff is. And I really mean we have no idea. So dark matter is stuff. It's something that's out there. We've seen that it's there, so we can't really probe it very deeply. Dark energy is what's responsible for making the universe explode. About 10 years ago, people discovered that after the Big Bang, the universe is not slowing down to come back into a big crunch. In fact, it's accelerating outwards. And so it's a huge, massive force responsible for accelerating the universe outwards, and that's what most of the universe, the energy and mass of the universe is. So the bottom line, though, is that we thought we made great progress in understanding what's out there in the universe. Turns out we were looking at a tiny, unusual sliver of what the universe is made of. Right? It's very humbling. So how do we know dark matter is out there? Well, there's a couple of ways. One is that you look at galaxies out in the sky, and you look at how they rotate. And the speed of something moving around a galaxy depends on the amount of stuff that's inside, because it's all gravitational, it's pulling it in. The more mass that's in the galaxy, the faster things should be going around. So what they did is they looked at the velocity as a function of the distance from the center of the galaxy, and what they expected was this curve. based on just adding up all the mass from all the stars they saw. And then they measured it and they saw something totally different. And that is a magical moment in science, right? When you discover that your theory is totally wrong. That's like a joyous moment because you're on the verge of learning something. It's a clue, right? Here is where you're wrong, and here's the first crack in splitting something open to getting understanding. It turns out nobody believed this data for like 50 years, though, because it was just seemed crazy. Because the only explanation was, well, maybe there's a huge amount of invisible matter out there, which nobody wanted to believe. It took a long time. But now we have lots of evidence of it. And in fact, you can even see dark matter out in the sky acting like big lenses, because dark matter can bend light if there's enough of it. And so if there's a big blob of matter out there in the sky between us and something else, then that matter can bend the light and act like a lens. And you see weird smearing effects in the sky due to that gravitational lensing. And so here, for example, this is from one of the comic videos. Imagine that you're here on Earth, and there's some galaxy far, far away, and there's a blob of dark matter between you and the galaxy. The light that comes out from the galaxy gets bent by the dark matter towards you. Light that coming out this way from the galaxy gets bent by the dark matter towards you. So if you look here, you see that galaxy. If you look here, you see the same galaxy in two different directions, right? That is a clue that there's dark matter lensing between you and the galaxy. So here, for example, you can see this galaxy in one place and the same galaxy somewhere else. So if you look up in the sky and you see two versions of the same galaxy, you know there's something between you and it acting like a massive, I'm talking a really massive gravitational lens. So that's also evidence that there's dark matter out there. In addition, we saw out in the sky, just looking, people saw this incredible thing happen, which is two galaxies colliding. Right now, I'm a particle physicist. I get excited when we take two protons and smash them together. Okay? This is an experiment on a different scale. Okay? Take two galaxies, smash them together. Astrophysicists don't get to design experiments, right? They don't say, let's build a galactic collider. But they get to look for them because there are experiments just happening out there. But they have to be lucky and find them. So here they were lucky and they found two galaxies coming together. Now every galaxy has normal matter and also has dark matter in it. And what happened is the two galaxies collided, the normal matter smashed into itself in mammoth collisions, just like you would expect, but the dark matter passed right through the other side. So the normal matter made a collision, but the dark matter just passed right through, so you separated the normal matter from the dark matter. You can actually see that if you look at this picture out in the sky. This red indicates normal matter, which is measured just by stars, and the blue is the dark matter, which is measured by the gravitational lensing. And so you can see that this was a mammoth collision, and the dark matter passed right through. So the dark matter, it's out there, it's heavy, but it hardly even interacts. Two galaxy-sized blobs of dark matter passed right through each other. Okay, so that's sort of humbling to remember that we've been studying this stuff in detail and publishing thousands of papers a year on a tiny slice of the universe. If your goal is to get some big picture understanding of how the universe works, then it's sort of like realizing that you've been studying the tail of an elephant for about 300 years. And finally, somebody walks you around to the front of the elephant and introduces you to the rest of it. It's a mind-blowing event, right? Now, as a physicist, your first inclination is going to be, well, I understand elephant tails, so I'm going to try and model an entire elephant out of tails, right? Maybe the rest of it is just a little perturbation on the tail or something. But what you really have to do is throw away everything you thought you understood and start from scratch, which again is one of the most exciting moments in science, right? Understanding that you know very little, being confronted with your lack of knowledge is the best thing in science because then you have something to do, right? You have an opportunity to learn. So that's why this kind of discovery is so amazing, because we know how little we know. Okay? So how do we make progress? How do we understand what the universe is made out of? What am I actually doing with myself, right? Well, if you want to understand how things are made, what you do is you take them apart. So if you're ever a curious child, maybe you took your toaster apart and you discovered it's made out of smaller elements, right? Screws and bolts and nuts. And then maybe you went on and took the blender apart and discovered that's also made out of screws and bolts and nuts. And you discover that your kitchen, the fundamental objects of your kitchen, are not appliances, but components of appliances from which you can build almost any appliance, right? So you've made a discovery. The fundamental description of your kitchen is not the appliance level, it's at the component level. Okay, so, excuse me, in particle physics we do something similar, and we use these colliders. There was a collider outside of Chicago at Fermilab, which is called the Tevatron, which is the most powerful collider until about 2007, 2008. And now the most powerful collider in the world is in Switzerland. It's called the Large Hadron Collider because it's large and it collides hadrons. It's at CERN, which is the European Center for Nuclear Research. And essentially, it takes the same idea, but says, let's not just take one thing apart, let's take two things apart simultaneously by smashing them together. Okay, so if we take our toaster analogy and extend it to the ridiculous level, what would happen if you built a toaster collider? Well, you take these two toasters, you speed them up, you smash them into each other, and you get a pile of parts at the end. And you say, well, I got 2 handles, so I'm going to guess there's 1 handle per toaster. I got 6 of these kinds of screws, so I'm going to guess 3 per toaster, right? And your basic assumption is going to be that everything that went into the collision came out of the collision, or that everything that came out of the collision started out in the collision in a different arrangement, right? And that's going to be one of your most powerful clues. In particle physics, we can't do that. It turns out what you can do when you have a particle collision is you take a lot of energy or momentum. So if you take, for example, something very small and give it a lot of energy and smash it together, you can actually make something new. So you can turn something which is very light but has a lot of energy, a lot of momentum, into something very heavy that moves very slowly. Because of this magical equation, you can turn energy into mass and back and forth. So we take very light particles, protons, speed them up to enormous energies to try to produce new kinds of particles. Okay, so what went into the collision doesn't have to come out of the collision. This is like modern day alchemy. We're turning one kind of stuff into new kinds of stuff. And you might think, well, that seems like a big disadvantage. It seems like it would be a big advantage to know that what came out of your collision was the same as what went in, because you could help understand the arrangements of stuff, right? Turns out it's actually our most powerful advantage, that what comes out of the collision doesn't have to have been made from what went into the collision. How can that be an advantage? Because it means you don't have to know what's out there in order to make it. As long as you pour enough energy, enough momentum into your collisions, you can make anything. All right? It's sort of like, there's a menu out there. There's a menu from someplace called Einstein's Cafe. And as long as you have enough energy in your collisions, you can look at the universe's menu of particles and say, anything I have enough energy to make, I will see it at the collider. So it really is a tool for exploration. You don't have to know what's out there in order to make it. You just pour enough energy into your machine, and you can make anything that has mass less than the energy you've put in. And this is why we try to build larger and larger and larger accelerators. Because the larger the accelerator, the more energy we can pour into the collisions, and the more new particles we can make. And this is why I think of it as exploration. So how much energy is in these machines? Well, this guy, a TeV is 1,000 GeV. And remember, a GeV is how much energy is in a proton. So this has enough energy to make 2,000 protons, or something that's as heavy as 2,000 protons. The one at CERN, we ran for a while at 8 TeV, so 4 times this energy. And in 2015, we'll turn it on again at 14 TeV. The exciting thing about turning on an accelerator at a new energy is nobody's ever seen this stuff before. You turn it on, you pour energy into these collisions, you have no idea what's going to come out, right? But you know very little about the universe, so you've got to be ready for surprises. And the way I think of it is an analogy, like imagine, so far before we turned on this accelerator, we used a 2 TeV machine and explored the universe in that sense, right? When we turned on the LHC at 8 TeV, it's sort of equivalent to simultaneously landing on 4 Earth-like planets, right? That's how exciting it was. Because you could find advanced civilizations waiting for you. You could find just piles of rocks. You have no idea what's out there. It's exploration. It's either going to be totally dull or amazingly fascinating in a way that revolutionizes your understanding of the world, the universe even, our place in it. So it's really an exciting moment. And I feel particularly lucky because I'm a pretty young guy. I wasn't around when they made the decision to start building this thing. Right? It was like in the early 80s when they decided to organize it and arrange it. And I was a tiny kid then. And the science that was happening to help us understand how little we know is also not I take no credit in that. But I happen to be here at this moment and have the facilities and the funds to use this amazing new tool that just came online to answer these incredible questions about the universe. So it's just really like a golden moment in particle physics right now. To know how little you know and have access to these awesome tools to help us figure it out. Okay, so what could you make? Well, this is a diagram we like to call a Feynman diagram after Richard Feynman, who made it up. And in these diagrams, time flows from left to right. And this axis doesn't really mean anything. But you have two particles that come in, and they follow these lines. And what happens here is these two particles come in, and then they turn into another kind of particle. Remember, I told you that what goes into the collision doesn't have to come out. These particles, they don't exist anymore. The stuff that was in them is gone. Their energy is turned into another kind of particle. All right? That particle doesn't live very long, and then it breaks out into two other kinds of particles. So you turn one kind of matter into another kind of matter. Right? Really, this is alchemy. Now you can turn normal everyday quarks into normal everyday electrons, or you could turn it into slightly less unusual muons, or, and this is the interesting thing, is you could turn it into something totally new, something surprising, something nobody's ever seen before. What could we see? Well, you have to look sort of back in the history of the universe to get a clue for what we might discover. Because these days, so this is a history of the universe from the Big Bang to the present day. Back in the era of the Big Bang, everything was pretty hot. These days, everything is pretty cold. I mean, it doesn't feel cold in California compared to the rest of the country this last few weeks, I know, but if you go out into outer space, it's pretty chilly, right? But it used to be that everything was pretty hot. The whole universe was a hot, dense plasma. There was a lot of energy density, even for making really heavy, weird particles. These days, the universe is mostly pretty cold and empty. You don't see these particles unless somebody artificially creates a lot of energy in a small amount of space, like we're doing with these colliders. So essentially, we're looking back in time to the Big Bang. We may be creating particles that haven't existed in billions of years. So that's pretty exciting. And you know, it opens up lots of possibilities, and people wonder, when we turn this thing on, people wondered, oh, you're going to create a black hole which might destroy the universe? And you maybe remember there's a lot of anxiety. This is one of my favorite cartoons, speculating that the beginning of our universe may have coincided with the end of the previous universe when they turned on their Large Hadron Collider. Fortunately, that didn't happen. Okay, so I talked a lot about why this is interesting and how we build these colliders and why that's useful. Now I want to tell you about what actually happens in the collisions. It's difficult to actually see the collisions because the particles we're talking about are super tiny. They're tinier than the wavelength of light, so you can't take a picture of them. And they exist for like 10 to the negative 20 seconds, right? So you can't like watch a video of it. Even best technology like scanning electron microscopes can't see these particles. So what do? Well, we build this collider. Here's a nice little movie of what happens. You zoom the particles up, and each of these is a little accelerator that gives it more and more energy to get ready for the next accelerator. And so it's a multi-stage thing. This is the SPS, which zooms these guys up to 450 GeV, and then it goes around the biggest ring at the LHC. And there are 4 points around the tunnel where these things, there's not actually any graffiti inside the tunnel. These things zoom around the tunnel, and there's 4 points when the particles collide. So they go in opposite directions around this ring, and at 4 points they collide. And so this is what's supposed to be a proton inside of the quarks. You see it zooming along inside this tunnel, and then it gets to the interaction point, which is surrounded by our detector. The detector is supposed to sort of take a picture for us. It's not a camera, but it's a massive piece of electronics that takes a picture of the collision. And so what happens is the two particles collide, and a bunch of stuff sprays out. And what we can do is look at the stuff that's sprayed out. And we see patterns, we say, oh, there's something here, and we try to deduce from those patterns what happened in the collision. And that is the goal of particle physics. And that's why we build these big detectors. Okay? And now each detector is very complicated. So you just saw a collision happening inside the detector. Now imagine a slice of the detector. So the beam comes in into the screen here, and it's another one out of the screen. The two particles collide right here and produce a spray of stuff. Now we've designed our detector in rings around this point of collision so we can understand the stuff that comes out. And each slice of the detector has a different job. One of them measures whether it has momentum, another one tries to measure their energy, another one tries to measure its direction, and each different kind of particle, a muon, electron, the kinds of stuff that flies out, leaves a different signature in our detector. So we can deduce based on the pattern of digital trails that each particle left in the detector what it was. We say, well, this was a photon, this was an electron, it had this direction, this much energy. So that's the kind of picture that we can build up of our detector. And these things are very complicated and very precise. Every time there's a collision, we read out data from 100 million sensors. Okay, and the collisions happen every 25 nanoseconds. So this is a huge amount of data, okay? And one of the most sensitive is at the very center, just very close to the collision. Okay, the very center of the detector, this thing has 140 million pixels to take a picture of what happened just the moment very close to the collision. So the Atlas detector, the one I work on, is at the accelerator just outside of CERN. Let me give you another picture of what the accelerator looks like. So here's the accelerator, right? And it's located next to Geneva, which is a beautiful place, in between two sets of mountains and this fields of sunflowers. It's a nice place to spend the summer. And the detector itself is 100 meters underground. And the reason it's underground is that in Switzerland, you don't have land rights more than, I think, 10 meters down. And so they can build this ring under people's property without having to pay them for it. And this is what the detector looks like, and you can see the scale of it. So this is a graduate student, and this is the scale of this thing. It's like the Borg ship. I mean, from here to here, it's like an 11-story building. Okay, and this was put together by a team of about 5,000 scientists. It cost lots of millions of dollars. It's one of the biggest machines mankind has ever made. Here's a better picture of it, and here's a graduate student for scale, right? So it's like 4 stories high, and like if you tipped it on its end, it would be 11 stories tall. And people have been working on this thing for years and years and years, starting in the 80s. And in the end of the last decade, it turned it on, and it actually worked. Right? And everybody was very excited. This is a picture from the control room when we saw the first collisions were actually happening, and everybody had been pouring their life into this thing. So the fact that it worked was very exciting. The Atlas collaboration, the one I'm a member of, has more than 3,000 physicists, and then there's more if you include all the graduate students, et cetera, from a lot of different countries, and all around the world, and everybody works together at CERN. It's really exciting to get to work with people from all over the country on such a big project. Every time we publish a paper, however, that means that there are 3,000 names on the paper, and the policy is to make it alphabetical. So I'm over here, and here is a Hungarian graduate student whose last name is A.A.D., and I won't try to pronounce it for you, but he's the first author on every single paper from Atlas. Congratulations to him. And the accelerator has been running really well, and if you measure, this is the date. See, so this is 2004, this is the month, sorry. This is the 30th day of the month, 4, 6, 8, this is a single year. And this we measure, it's called luminosity, essentially the number of collisions we've managed to accumulate. And you see that things are going well, they take a break to fix something, things are going well. And anyway, this number is climbing. And the more collisions you get, the more chances you have to see something interesting. Okay, unfortunately, interesting things are very rare. So we have a very high collision rate, like 10 to the 8 collisions per second. Okay, that's a lot of collisions every second, 10 to the 8. But and only occasionally you'll see something like a W boson or a Z boson or a top quark. A Higgs boson, it takes 10 seconds of running at this rate before you make one Higgs boson. They're very rare. So mostly the stuff that happens is pretty boring stuff. You have to run for a long time to see something interesting. Okay, so what is this Higgs boson? Finally working after this question. You've heard a lot about the Higgs boson. Why is it important? Why is it interesting? Well, it certainly has gotten a lot of press. When it was discovered, it got a lot of hyperbole in the press, collisions that changed the world. In the New York Times, they said, physicists whose collective efforts created the Large Hadron Collider and have revealed the deepest layer of reality our species has ever probed. Wow, that sounds pretty cool, even though I don't really know what it means, the deepest layer of reality. But what is the Higgs? Well, remember I told you that we're interested in this question of mass, right? Why do particles have different mass? What is mass anyway? Well, the Higgs particle is the one responsible for assigning the mass to different particles. It's the reason why one particle has a lot of mass and another particle doesn't have a lot of mass. Okay? So, but what do I mean by mass, right? And an hour ago we heard the description of mass basically as mass is stuff. Mass is the amount of stuff in something. And that's fine for a macroscopic experiment, right? You're going to talk about medicine balls versus beach balls. It's correct, right? There's more stuff there. But what about when you're talking about a fundamental particle? What does mass mean when you're talking about a particle? Because particles are points. They don't have volume. In our theory, these particles have no spatial extent. So what does it mean for one to have more mass than another one? It's not like there's more stuff packed in there, right? It turns out mass is just a characteristic of fundamental particles, the way electric charge is. Some particles have charge, like electrons. Some particles don't have charge, like neutrinos and neutrons. It's just a label you attach to the particle. It has a lot of mass, it doesn't have a lot of mass. In fact, you can think of it as sort of a different kind of charge. You like to think of electric charge as a characteristic a particle has. A mass is sort of like gravitational charge. If two particles have a lot of mass, then gravity pulls them together. If they don't have mass, gravity doesn't pull them together. Interesting about gravity, though, is because there's no negative mass particles, you have no repulsive gravity, right? Gravity is only attractive, which is one thing that makes it very interesting. Okay, so then what does mass mean? Well, mass still has the same connotation that you heard about. If something has a lot of mass, it's hard to speed it up and hard to slow it down. If something has a very small amount of mass, it's easier to speed it up and easier to slow it down. Why is that? Well, the Higgs field, so there's two parts to the Higgs boson. There's the Higgs boson itself, which is a particle, and then there's the Higgs field. The Higgs field is something which permeates the whole universe. Like back in the 1800s when people talked about the ether. The Higgs field is something which fills the whole universe, and every particle feels it. But different particles feel it a different amount. So if a particle feels the Higgs field very strongly, then it has a lot of mass. The Higgs field makes it very hard for something to speed up, very hard for something to slow down, if you feel the Higgs field very strongly. If you can ignore the Higgs field, like a photon, which has no mass, then it's not hard to speed up and it's not hard to slow down. So the Higgs field is responsible for giving these particles mass because it's the reason it's hard for things to speed up or slow down. Okay? But the question remains, why do different particles feel the Higgs field differently? Right? This answers the question of why particles get mass. It doesn't answer the question of why different particles have a different amount of mass. It just changes the question from why do particles have different mass to why do particles feel the Higgs field differently. Okay? And we know that particles have very different amounts of mass. Electrons have almost no mass, top quarks have a lot of mass. So this is still an open question. Even though the discovery of the Higgs boson tells us that the Higgs field is what gives particles mass, we still don't know why there's a Higgs field and why some particles feel it more than other particles. So how do we actually see the Higgs? Well, we see the Higgs by making it. And we make it by taking our collider and slamming stuff into each other, and sometimes the Higgs comes out. The problem is, as I told you earlier, Higgs doesn't last very long. It lasts for 10 to the negative 23 seconds. So we can't actually see it. What we see is the stuff that Higgs turns into. And one of the most common things for the Higgs to turn into is, for example, two boson quarks. It can also turn into two photons or two Z bosons. Okay, so what we do is we look for those things that Higgs can turn into. We try to find in our trillions and trillions of collisions that look just like the Higgs boson. The problem is, for every time you make a Higgs boson, right, like this one, that turns in this case into two boson quarks, there's lots of other ways to make two boson quarks. In fact, the other ways to make the two boson quarks are much more common than the ways to make Higgs boson. So you have to somehow not just see that there were two boson quarks, but figure out which ones came from the Higgs. So this is a very tricky problem, and we do it statistically. So we have two theories. We have a theory that says this is what you would tend to see if there were no Higgs bosons. Right? So there's lots of other ways to make collisions of a certain amount of energy, right? Like I showed you in the previous slide. And if there is a Higgs boson, you would see a little blip in this curve, because all the Higgs bosons would pile up at the same energy. The problem is, and you can barely see it on this plot, is that the difference between these two predictions is very, very small. because you have a lot of other stuff that looks like Higgs bosons, and the Higgs bosons themselves are very rare, right? So we call this the background, the stuff that looks just like the Higgs bosons, and this signal sits on top of the background. So how do you distinguish two hypotheses that have almost no difference in their prediction? You need a lot of data. Okay, you need to take a lot of measurements to see the difference between these two. So that's why we run this thing. In the comic we say, open 24 hours, over 1 billion collisions served. We run this thing 40 million times a second, all day, all year long. That means there are people sitting in the control room there, even in the middle of the night at 3 a.m., running this thing, because you need a lot of data to separate these two hypotheses to know which one is the right answer. So what I'm going to do is show you the actual data. So that was the accumulation of the data from the beginning of the accelerator to the end. You see how it builds up, and there's a lot of statistical fluctuation, and in the end, these are our two hypotheses. The blue line is what we would have expected to see if there was no Higgs boson, and the red line is what we expect to see if there is a Higgs boson right here at 125 GeV. Okay, and it's maybe not totally overwhelming to look at, right? But this is the evidence that persuaded us that there is a Higgs boson in the universe, right? These handfuls of collisions, this is amounts to about 300-400 collisions taken out of trillions and trillions and trillions that look like evidence for a Higgs boson. This is where a Higgs goes to two photons. What you do is you take the energy of the two photons, you add them together, and that's what this is a plot of. The Higgs can also go to other stuff. For example, the Higgs can go to two Z bosons, which then decay into different leptons. And this is the top of the histogram here is what you expect with no Higgs boson, and then this blue part is what you expect from the Higgs boson. And you see here's the data from the collider. It tends to agree with the Higgs boson hypothesis more than it tends to agree with the no Higgs boson hypothesis. So here's the peak right here. So I hope I've convinced you that we're in an exciting era in particle physics. I like to think that 200 years from now, people will look back and say, wow, that was really the moment when we understood the first XYZ mysterious answer about the universe, which changed our understanding of the universe and our relationship to the rest of the universe. I think back at the development of quantum mechanics. I think, wow, that was really interesting. I wish I'd been there at that time to help figure that stuff out. But here we are poised at perhaps an even larger revolution in our understanding of the way the world works. Now, if you're worried about the continued running of the LHC, there's a website you can check. It's called Has the Large Hadron Collider Destroyed the World Yet.com. And I promise it's constantly kept up to date. You can check it at any moment. And if you're interested in learning more, I do have these webcomics which try to explain dark matter and the Higgs boson and other stuff. You can see them on my website here. So I hope you've enjoyed that, and I'm happy to answer questions afterwards. Thank you very much.